My name is Jimmy Yang. Today I will talk about a theory that is proved by me. Consider an elliptic curve E of supersingular property. That is supersingular elliptic curve defined over fp squared minus fp. That is the J invariant of E of the supersingular elliptic curve belongs to fp squared, except for fp. So the points is defined over fp squared, that is the finite field of order p squared, where p is a prime number. But the J invariant is not defined over fp, that is a finite field of order p, where p is a prime number. We consider this setup, and then we consider n torsion group of elliptic curve, and we want to have a property that n divides p plus 1. So n is less than p, and n divide p plus 1. So in this setup, we understand that E parentheses fp squared parentheses, that means all of the points that defined over fp squared is isomorphic to cp plus 1 times cp plus 1, where cp plus 1 means a cyclic group of order p plus 1, where C means a cyclic group. So from a theory that doesn't prove here, we know the property that E parentheses fp squared f parentheses, that is all of the points that are defined over fp squares, and also defined over the elliptic curve E, where E is a supersingular elliptic curve. Then E fp squared, that is E of fp squared, where points defined of fp squared is isomorphic to a direct product of a cyclic group, where the order of the cyclic group is p plus 1. So the number of points of E fp squared is equal to p plus 1 times p plus 1. Okay. Now, I will continue to talk about the property here. We consider twist of elliptic curve, E twist. What is a twist? Twist means that the J invariant is the same, but the model is not the same. So E is defined over fp squared, and E twist is also defined over fp squared, because the J invariant of E and E twist are the same. So both E and E twist are both defined over fp squared, but the fp squared model of E and E twist are not the same. The model means a polynomial which defines an elliptic curve such that the solution of that polynomial, it means that if we set that polynomial equal to 0, so fp squared model are not the same. This is the definition of twist. The J invariant are the same, but the model of FP square model is not the same. Okay. So what are the points defined over FP square if we consider E twist? What are the points of E twist which are also defined over FP square? Do you understand? Okay, now I will give you a theory here, which I will not prove it. E twist FP square is equal to CP minus 1 times CP minus 1. Okay. So E FP square is equal to CP plus 1 times CP plus 1. And the E twist of FP square is equal to CP minus 1 times CP plus 1. Okay, now I will ask a question. What are the intersection of E parentheses FP square parentheses intersect with E twist parentheses FP square parentheses. So what are the points that are defined on FP square, which are also the points defined over elliptic curve E, but also defined over elliptic curve E twist? That is, the kind of point holds the following three conditions. First, it is defined over FP square. Second, it is defined over E. That is, it is the points of E, and it is also the points of E twist. So, are there any points that satisfy three conditions? The first condition is that it is defined over FP square. Second condition is that it is defined over E, elliptic curve E, and also it is defined over E twist. So what are the points which are the intersection of E parentheses FP square parentheses and E twist parentheses FP square parentheses? The results are disclosed by P. Clark in a paper called Elliptic Curves over Real Number Fields, and in Section 2, Preservation of Torsion Subgroups under Base Extension Theorem 2.1.c. AT parentheses F parentheses TOS is equal to AT parentheses F parentheses of two torsion group is equal to A parentheses F parentheses of two torsion group. That is, the two torsion groups are not only defined over F, but also defined over AT, but also defined over AF. So, two torsion subgroups satisfy the following three conditions. It is defined over F. Second condition, it is defined over A. Third condition, it is defined over AT. AT means the twist of A. Okay, the proof are the following. we consider monomorphisms, that is multiple monomorphisms. We consider all of the monomorphisms. We consider a series of monomorphisms from A of f to A of f extended by square root of t. And we consider another series of monomorphisms, that is from at of f to a of f extended by square roots of t. Then the extension are the two torsion subgroups. So we get the result that in the finite field, E defined over fp squared. If there is a torsion subgroup defined over fp squared, then it is also the points defined over E and E twist. Okay, so consider a supersingular elliptic curve defined over fp squared minus fp. Then E supersingular elliptic curve and the E twist supersingular elliptic curve. The intersection of E super and the E super twist and the intersection with fp squared. The three intersection of fp squared and the E sup and the E super twist that are two torsion subgroup of E. Okay. Thank you very much. You can see the theorem here proved by P. Clark. Bye-bye.